that's really been central to mathematics for centuries.
Mm,
How do you find the exact solutions, the roots of a polynomial equation?
right.
We all remember the quadratic formula, for x squared equations, but what about, say, x to the fifth
Mm,
or x to the 18th? It gets complicated really
it really
fast.
does. It's a fundamental challenge, and it quickly runs into some major roadblocks as the highest power of x increases.
Exactly.
Hmm.
And today we've got this stack of source materials, some journal excerpts, publications, and they all focus on a particular approach. The discriminant formula of Mourad's Sultan Ezouidi Hism.
Okay.
So, our mission in this deep dive is basically to understand what these specific documents say this formula does, how they describe it working, what makes it stand out. But, and this is important, we're sticking strictly to the information provided right here in this source material.
Got it. We're just unpacking what's presented in these pages.
So, let's set the scene a bit. Why is finding the roots of polynomials, generally speaking, such a persistent problem? What makes getting those exact answers so tricky?
Well, one major difficulty, and the source points this out, is moving beyond just getting approximations.
Okay.
Methods like Newton's method, they're powerful for getting close to a root, but they're iterative, meaning they kind of refine an estimate step by step.
Right, you inch closer.
Exactly. And they need an initial guess to start. Choosing that starting point, that can be non trivial. Plus, they usually give you a decimal approximation, not necessarily the perfect exact mathematical value.
Okay, so great if close enough works, but maybe not for finding the precise mathematical bullseye. What about finding different kinds of roots, like not just simple numbers?
Yeah, that's another challenge mission right here in the source. A method like the rational root theorem, for instance. It's helpful for identifying potential roots that are fractions rational roots.
Hmm.
But lots of polynomials have irrational roots, like the square root of 2 or complex roots involving I, the imaginary unit.
Right, the weird ones.
Well, yeah. And traditional algebraic methods often need different strategies for these. The rational root theorem isn't really built to find those easily.
So the core problem is finding all the roots, real, irrational, complex, even roots that show up more than once, what mathematicians call multiplicity,
Yes, there are multiplicity.
and finding them exactly, especially when the equations get long and messy.
Precisely. And this is where this discriminant formula, as it's detailed in our source material here, comes into the picture. And it comes with some pretty significant claims.
Okay, lay them out for us. Based purely on what you're reading in these documents, what does this formula claim to do that sets it apart from those other methods we just talked about?
So the core claims presented in the source are, well, they're quite ambitious. First off, it asserts it can give you exact solutions. For all types of roots, irrational, complex, even repeated roots. No approximations needed, and it supposedly handles them all together.
Exact roots for everything. That's a big statement.
It is. Second, the sources claim it has general applicability. It's presented as working for polynomials of any degree.
Any degree.
Any degree. The publications list even mentions using it for really high degrees, like an 18th degree polynomial, alongside the simpler examples they show.
An 18th degree. So from quadratics way up to,
All right.
well, anything.
That's the claim being put forward right here in these documents, yes. Third, and this is a really key difference from something like Newton's method, the formula apparently does not require any initial guess.
Huh. So you don't need to hunt for a starting point.
Nope. You start directly with the polynomial equation itself. Just feed it the equation.
Okay.
The source describes it as working by using the polynomial's own structure, its coefficients, directly. And it's also claimed it determines both the nature of the roots, like are they real or complex, and their exact multiplicities.
Knowing the exact multiplicity, how many times a root appears, that's definitely useful information. So, okay, general, exact, no guess needed, works from the structure, gives multiplicity. That's quite the list.
Mm-hmm.
How does it actually work though? Conceptually, I mean, based on the description here, I'm seeing a lot of complex looking math notation in the source.
Yeah, the detailed math involves calculations based on certain values derived from the polynomial's coefficients. The source labels them things like LQ and SOR.
Okay.
Now, while the full notation is dense, the idea that seems to be presented is that these calculations perform a kind of transformation, or maybe a simplification of the original polynomial equation.
A transformation, like morphing something complicated into something simpler to solve.
Yes, that seems to be the described approach. The goal is to manipulate the original polynomial, px, using these coefficient based calculations, and arrive at formulas or maybe simplified equations whose solutions directly give you the exact roots of the original one.
Ah, I see.
The examples in the source, they show polynomials simplifying into forms like, say, x to the fifth equals some constant k, or reducing a high degree polynomial in x into a lower degree one in maybe x squared.
Okay, so these specific calculations, using values cooked up from the polynomial itself, they lead you to a form you can actually solve directly.
That's the mechanism described in the source material, yeah. It appears to be presented as a systematic process based on the polynomial's inherent structure.
Let's maybe dive into some of the specific examples they give in the source material because they really seem to illustrate these claimed outcomes. There's a fourth degree example here.
Right. The source starts with this one: px x of xxn plus 360xx plus 2160xx plus 6480 equals 0.
Okay.
It then shows how applying the formula, calculating these x values they mentioned, results in a significant simplification. It says many terms essentially drop out or combine in a specific way.
Leaving px equals x out plus 360 xxx, 89640 xx plus 265 680 equals 0. And then the roots are just given in this specific form using complex exponentials. It says x-axis 0, 1, 4, 3, 1, 4, 4, 4 plus 6 plus 6c raised to 2k plus 195.
Wow. Okay, that original polynomial looks pretty gnarly. Like it would be tough to factor just by looking at it.
Yeah.
And it simplifies down like that.
Yeah.
And the roots are given precisely, including complex numbers using Euler's formula. That's the e to the I pi stuff.
Yeah.
That structure tells you a lot about where they sit on the complex plane.
It does. The source then gives some fifth degree examples. There's one, px equals x on 30x samples plus 360x on plus 64.8x equals 0.
Okay.
Here, the calculations are shown to lead to a form where only the XOR and a constant term related to this x4q value remain.
Wait, so it just becomes XOR equals some number. Okay,
Yeah.
XOR is S4Q. That's
Yeah.
about as simple as you can get for a fifth degree.
Exactly. The source shows that this S4Q value works out to negative 24,300,000. So you're left solving XORing Agnes 24,300,000.
And the roots are then given directly using the fifth root and those complex exponentials again. The 5 exact complex roots just sort of fall right out.
Huh.
There's another fifth degree example shown, slightly different coefficients, and it results in xu equal minus 35u, which again is very direct. The roots are given as vec 0, 1, 1a, and 2, 3, 3, 8, 4 equals 7 plus 7 to the 2k plus 1i5. And the source explicitly labels these exact roots found using discriminant formula.
Seeing that kind of simplification in the examples, turning a dense polynomial into something basic like xo equals a constant, it certainly makes the source's claim about finding exact roots directly feel, well, more tangible. The source also includes higher degree examples too, right? I think I saw up to degree 10.
Yes, absolutely. For instance, some 8th degree examples are shown. There's one like x year plus 36 at O plus 446 at euro plus 2196 x I plus 3465 exudes 0. Notice only even powers of x appear.
Okay. Xio, Xio, X.
Right. And the method, as is described here, lets you treat this as a 4th degree polynomial just in terms of x there. You make a substitution, like let x at O's. The source provides the roots for x, native 3, native 7, native 15, and then gives the corresponding roots for the original x. They are 3i, 7i, 11i, oval 15i, purely imaginary complex roots in this case.
So it can effectively slash the degree of the problem if the polynomial has that kind of symmetric structure, turning an 8th degree into a 4th degree using a transformed variable.
Exactly, based on the structure of the polynomial itself, according to the source.
Mm-hmm.
There's another 8th degree example. Take O plus 35 out of double E 50x of 4 equals 24 equals 0. Same idea. It reduces to a 4th degree equation in xx takes x, which is x as an x6 plus 35x on 50x plus 24 equals easy as a way down.
Okay.
This time the source gives the roots for x as 1, 4, 2, and 3, which then leads to real and irrational roots for x, tame boy O and I2, and an a is 3.
So that example highlights finding different types of real roots integers and irrational square roots.
Precisely. It seems designed to show the method handling various cases.
It feels like it's covering all the bases shown in these examples, real, irrational, complex. What about those 9th and 10th degree examples mentioned?
Yeah, the source provides examples there too, illustrating similar kinds of simplifications. There's a 9th degree one, xx Ushidura's reach, plus 11x6 600. See the pattern. Powers 9, 6, 3.
Multiples of 3.
Exactly. So it's shown to become a 3rd degree equation if you let x is x0. The roots for x are found 1, 2, 3, and then the roots for x are the cube roots of those.
Okay.
Another 9th degree case mentioned is shown to simplify even more drastically, just to x air equals 99.
Wow.
And for a 10th degree example, something like x euro 105 by a mat 1 plus 10 ear equals a 50, the source shows how letting air xx transforms it into a quadratic in y. y over 5y plus 10 near equals 0.
So a 10th degree becomes a quadratic, which we know how to solve exactly.
Right. The roots for air are then found using a formula that involves some of those coefficients from the original polynomial, and from that, the roots for x are derived.
These examples, I mean, as they're presented here in the source, they really paint a picture of a method that systematically uses the polynomial's coefficients and structure to either simplify it dramatically or cut it down to a solvable lower degree form. And it seems to consistently yield exact roots across these different degrees and root types shown.
That certainly appears to be the key mechanism being described and demonstrated in these documents.
Okay, so let's bring it back to the bigger picture then. What does this discriminant formula, as described and claimed in the source material we have, fundamentally offer compared to, say, the previous general approaches to polynomial solving that we know about?
Well, based strictly on these documents, its main contribution or claimed contribution is this idea of a single general method that provides exact roots for any polynomial degree.
Right.
And that directly contrasts with numerical methods, which give approximations, or the traditional algebraic formulas, which, historically only existed up to degree
The
4.
quartic formula, yeah. Nothing general beyond that, usually.
Right, exactly. The source emphasizes that this method finds all root types automatically real, irrational, complex, repeated, and critically, it eliminates the need for that initial guess. It works, supposedly, solely from the polynomial's inherent structure.
So it's being presented here as a kind of universal exact solver for a problem that, well, has historically been considered unsolvable exactly in a general way for degrees 5 and higher, Abel-Ruffini theorem and all that.
That is precisely the magnitude of the claims being made within the source material, yes.
And the documents provided, they also include that list of publications by the author Mourad Sultan Ezouidi Hizm.
That's right. It lists published work that apparently explores this discriminant formula for very specific degrees. Degrees 4, 6, 18 are mentioned, and also the general case, degree n,
Okay.
which seems intended to reinforce the breadth of the claimed applicability that's presented in the main text we've been discussing.
So wrapping up this particular depth dive, focusing only on the source material, we've looked at the historical challenge, as described here, of finding exact roots for polynomials and the limitations of some traditional methods mentioned.
Mm-hmm.
We then dove into this discriminant formula of Mourad Sultan Ezouidi Hizm, which is presented in the source as a novel general method. The claim is it finds exact roots for polynomials of any degree, any type, no initial guess needed, just by transforming the equation based on its structure and coefficients.
Yes, and we've really focused entirely on reporting what this provided source material claims the method does
Yeah.
and how it describes achieving those results, including walking through some of those illustrative examples they provided.
It definitely makes you pause and think, though. If a general method like this, one that claims to give exact roots for polynomials of any degree, if that's indeed the case as it's presented in these sources, what might that actually imply? For fields across science and engineering that really rely heavily on solving high degree polynomial equations to model complex systems,
That is the profound question these source documents seem to invite the listener to consider, isn't it? What would that really mean?